about the algebraic theory of quandles. Let's welcome.
Right, thank you very much for the invitation. So I would like to tell you about the algebraic theory of quandles we try to develop. And I will start with a motivation from knot theory, but myself, I'm not a knot theorist, I'm an algebraist. So I'm always interested in applications, what we do. I mean, we do the theory of quandles from purely algebraic point of view. I mean, we are interested in the theory as it is, but of course, I'm aware of the not theoretic applications. Yeah, I'd like to learn always if there is some more interesting connection than what I already know. So I will start with the quandle coloring of knots, which maybe many of you know. So I will go very briefly through the motivation, and then I will switch to the algebraic theory of quandles from various aspects. So our main...
excuse me, dear colleagues, please mute your microphones unless you really have a question, okay?
Yeah,
okay, let's proceed.
So my main interests, the main tools we use is either group theory or universal algebra, maybe a little bit surprisingly, so I will focus on these two things. And occasionally I will tell some occasionally...
Okay, excuse me.
Occasionally, I will tell some connections to knot theory whenever I know about something. Let me start with the knot coloring briefly. So I guess everybody knows what is the three coloring of knots. You have three colors, and you are coloring arcs of a knot diagram. And the condition is that at every crossing, you have either one color or three colors. Okay, so it's forbidden to have two colors at a crossing. Well, and if you count the number of non-trivial colorings, then this is a not invariant. This number is invariant with respect to the Reidemeister moves. Okay, and by non-trivial coloring, I mean more than one color, because every diagram can be colored with a single color. Okay, and so this is the most basic one, and there are many variants like the n coloring. So we have n colors, which are represented by numbers between 0 and -1. And the condition becomes slightly more complicated. So the condition which is actually invariant is that you calculate twice the color of the bridge, and you sum the color of the left and right underpasses, and you compare these numbers modulo n. Okay. So again, I mean, this if you count the number of non-trivial colorings, then this is invariant with respect to Reidemeister moves, right? Well, so one would wonder what is the general pattern, right? How many conditions like that can you find out? How many invariants are coming in from arc coloring? So here is an abstract setting. Okay, so you have just a set of colors C, and you have a ternary relation because, well, first of all, you consider oriented knots. So the coloring which I was talking about well, doesn't depend on orientation, but in general, you want to talk about oriented knots so that you have the bridge and you have the left and right underpass. Okay. So then you have a ternary relation, and you want to compare the three colors which meet at each crossing in a certain concrete order. So let's say that the triple means the bridge, the right underpass, and the left underpass. Okay, and the ternary relation T will collect all admissible triples of colors. Okay. So I impose that at every crossing, when you have the three colors, then this triple has to be in the ternary relation. Okay, so for example, what I was talking about on the previous slide, so you have n colors, so you have numbers between 0 and -1, and the ternary relation will be just 2x equals y plus z, and you calculate modulo n. So now the question is, I mean, when do you get an invariant, right? So for certain carefully chosen sets of colors and relations, you get an invariant, and in general, you almost never get an invariant, right? I mean, for a random ternary relation, you get nothing interesting. Okay, so the question is which relations provide a not invariant, and what I want to do is so either it's a decision problem, there is a non-trivial coloring, or there is none. So the answer would be yes, no, or what is even more interesting from the computational point of view, you count the number of colorings. Okay, so let me denote by that the number of colorings of a given knot, or the given diagram, actually, I should say, if it's not invariant. So the number of colorings with respect to a given ternary relation. Okay, and I'd like to have this to be an invariant. So this is a solved problem, and it's. I'm not sure when this was. I'm not sure when this was noticed explicitly in this form for the first time. Maybe it was in a paper by Fenn and Rourke, but essentially this idea is in the original papers where quandles were introduced by David Joyce and independently by Sergei Matveyev in 1980s. And one can prove using the ideas in these papers very easily that I mean, the ideas from the papers are not that obvious, but once you know the papers, then it's easy to prove this fact in the present form, which means that the coloring is invariant if and only if T is a graph of a Quandle operation. Okay. So what do I mean by a graph of an operation? So we have two parameters. So if you have an operation star, then the triple would be x, y, and x star y. Right? This is like a graph of a normal function in analysis. You have x and f, you have pairs x and f of x. So here you have triples x, y, and x star y. Okay, so in this sense, the graph of an operation. Okay, so in order to be invariant, you have to have a graph of an operation, and this operation has to satisfy three relatively simple conditions. Okay, the first condition is so-called idempotence, that the operation should satisfy x times x equals x. The second condition is related to the fact that it's a graph of an operation, so it's a unique division. Right? So the fact that it's a graph of an operation means that if you have x and y, then the third coordinate is uniquely determined. Okay, and the second condition essentially says that if you have that in this ternary relation, if you have the first and the last coordinates given, then the second one, the middle one, is uniquely determined. Okay, and algebraically, this is a unique left division. Okay, and the last condition is something which is called self-distributivity. Well, and the three conditions actually come naturally from the three Reidemeister moves, as I will show quickly on the next slide. Okay, and it's really an if and only if statement. So if these conditions are satisfied, then you have an invariant. I think this is well known. But you have also the other implication that there are no other possible coloring invariants, which is maybe less known, but it's not difficult to prove. Okay, so algebraic structures of this sort are called quandles. So they're axiomatized by these three simple axioms. And I will talk about quandle coloring, and the notation will be with Q as an index. Okay, so that's the connection of quandle theory to knot theory. And here's the connection of the respective axioms to Reidemeister moves. So essentially, just very briefly, where the ideas come from. So if you have the first Reidemeister move, then, since the number of colorings shouldn't change when you perform the first Reidemeister move, then, if you have a plane arc, then let's say its color is x, and when you have a single loop, then the color will be imposed will be x star x by the condition. Okay, so should the number of colorings be the same? I mean, these numbers should be equal, and the other way around, right? Briefly, so that's where the idempotence comes from. Well, if you have the second Reidemeister move creates an extra arc, which is supposed to be colored somehow, and if the number of colors shouldn't change, then this must be uniquely determined. Okay. Uniquely determined, and also this one and that one should have the same color. Well, so that's essentially the condition that first of all it's a graph of an operation, and that this operation is uniquely divisible. Well, and the third Reidemeister move is actually equivalent to self-distributivity. Okay, if you just assign colors correctly, then you will notice that the bottom strand in one picture is the one side of the self-distributivity, and on the other picture is the other side of the self-distributivity. So So this is a brief explanation where the axioms come from, that they're closely related to Rademacher moves. Okay, so this is just the idea, and this has to be turned into a proof, but formal proof. But that's essentially the main thing. Okay, so if you want some nice coloring invariants, then you need some nice quandles. If you want to tailor your invariant to particular needs, then you need quandles with particular properties. So we are interested in constructing as many examples of quandles as we can, and also in classification of various classes of quandles and enumeration and things like that. And we hope that providing sufficiently many examples, not theorists will be able to pick whatever they need for their considerations. Okay, so that's roughly the idea of the connection. Well, and so from the computational viewpoint, if you want to solve on a computer algorithmically, if you want to solve knot equivalence, so you have two knot diagrams, and you want to decide whether they represent the same knot, then well, what you can do, I mean, given a family of quandles, then you can run over each quandle from this family, and whenever you calculate the colorings, and whenever the colorings disagree, then you have a certificate that these are different knots. Well, and if you run out of the quandles in your family, then you just say you have no idea, right? So
excuse me, I have a comment. Actually, there was a beautiful talk by Konfeimer and Mrovka at the last ICM. That was a plenary talk which can be easily found on the YouTube. They dealt with the conjugacy operation on groups. Actually, this is more or less the same. For the group SO3, SU2, this is more or less the same as just this reflection in geodesics. And actually, this was the starting point from which is related to the Hovanov homology, and which is used to prove that the Hovanov homology is an unknown detector. So here you deal with some groups, but actually groups can be considered not only discrete, but also we can consider some modular spaces of representations, and those can detect the unknown in particular.
Right. So I will actually, so later in my slides, there is a distant connection to this Kronheimer and Mrovka theory, but so I will come to that a little bit later. But if you want to have something which is reasonably computationally efficient, then you want your structures as simple as possible. So then actually discrete groups, like small finite groups, are maybe more suitable for calculation than these complicated things such as the Hovanov homology. So one thing is that something classifies the unknown, for instance, in theory, like it's a complete invariant, but it's not if it's not clear how to calculate, then from algorithmic viewpoint, it's kind of useless. Okay, so yeah, so I'm in. So my background is to a big extent in computer science. So like from purely computational viewpoint, this is actually a relatively efficient way to deal with the knot equivalence problem. Okay, and we actually did some experiments. So with my colleagues Andrew Fish and Alexei Lisica, we actually programmed the whole thing, and we experimented with various families of quandles. And we have to say that the algorithm works pretty well in practice. So like if you have small inequivalent knots, like maybe up to 20 crossings, maybe 30 crossings, then we can quickly find some small quandles such that the number of colorings is different. So like in general, as a mathematical theory, I mean, we don't know how to use quandle coloring in some deep way, but from purely computational view, like write down a software which actually calculates something, this is actually pretty good. Okay.
So about how many quandles, I'm sorry, David, how many quandles do you use?
So what did we use? So we used all connected quandles up to size 42, because there is a library of them. And then we used simple quandles up to maybe 100 elements. And that was pretty much it. So
but so say to distinguish the first 1.7 million knots. Do you have a rough estimate of how many quandles were used?
So I think so most knots get distinguished very quickly. So first of all, you should start with let's say Alexander quandles or these affine quandles, and then these will already distinguish most of the knots, right? I mean, if the knots have different Alexander polynomials, then very quickly you will find Alexander quandles which distinguish these two. So, but it's equally difficult to calculate the Alexander polynomial. So this problem is actually interesting only for knots which have the same Alexander polynomial. Well, and then actually, usually very quickly you find a non-affine or non-Alexander quandle which distinguishes them. Well, but this is just empirical observation.
Yeah, sure.
So I assume that quickly you can find examples, or maybe not quickly, but you can find examples of knots which totally fail this way, but they will have a relatively large number of crossings. Okay, so in that sense, and there is some theory which says that this is not doomed to fail. Like if Q contains all, let's say, finite connected quandles, then sooner or later, if you have non-equivalent knots, then you have to find different colorings. But there is no theory which says what is the smallest quandle that needs to be used to distinguish the knots. Right. So we only have empirical evidence that this never lasts too long. Okay. So. Okay, so that's one of my motivations, just to calculate it efficiently, but I mean in practice. So for some randomly generated pictures. So for that, this is not hopeless. But still, I mean, you want a nice set of quandles to work with. The efficiency certainly depends on the set of quandles that you use for coloring. Okay. Well, so we are back to the same problem. I mean, constructing as many examples as you can, and then maybe run experiments which quandles work well, or actually even better prove something. Okay, so the next part is, so I will go quickly over a few classes of quandles, which, I've seen that you already had some quandle talks on this seminar, so you are probably aware with all of these examples, but anyway, I want to mention briefly. So, okay, so back to the definition, okay? A quandle is an algebraic structure with a single binary operation which satisfies these three axioms which are already mentioned in the theorem. And equivalently, you can state it in a neat way, which somehow shows that this should be a natural notion in mathematics, not only in knot theory. So one condition is this idempotence, and then the other two conditions can be actually translated like this. So consider so-called left translations. So these are mappings, so X is fixed, and then it's a mapping from Q to Q, which takes Y and assigns to it X times Y, okay? So for each element of the quandle, you have one left translation. Or in the context of quandles, actually people use the notion left inner mapping or inner mapping, but like this is a general notion for any binary algebraic structure. This is an interesting notion. Okay, so let me call them left translations. Well, and the self-distributivity says that this is actually a homomorphism from Q to Q. Okay, this condition X times star YZ equals XY XZ. This is exactly the expression that this is a homomorphism. Well, and the second condition, this unique division, means that this is actually a bijection. Okay, so these are algebraic structures where all left translations are automorphisms. This is a very natural condition, right? I mean, these kinds of structures should appear elsewhere in mathematics too, right? So there are some natural examples like conjugation quandles. Take a group and take the operation of conjugation. This is a natural example of a quandle. Okay. Another natural example is an affine combination of two numbers on any module or abelian group. So take an abelian group and take an automorphism and take an affine combination using this automorphism. Right? This is another very natural condition which defines quandles. Okay, and then there's plenty of constructions. I will mention some of them later, but these are maybe the two most famous ones. And quandles appear elsewhere in mathematics. As I said, it's natural to expect so. So you might have seen quandles if you do symmetric spaces in geometry, or it somehow naturally appears in braid theory, in Hopf algebra. So something so quandles can be considered as a special case of set theoretic solutions of the Young-Baxter equation. Shouldn't be surprising.
Excuse me, what do you mean by knots? So do you mean that there are quandles on the set of knots?
No. I mean, it appears in knot theory. Like it's so this definition naturally appears in knot theory, in braid theory, in this theory of symmetric spaces when you try to describe symmetries of certain manifolds.
Yes, and you know the example with this conjugation in the SO3 is just reflection. So we can consider not only discrete quandles, but also also there's continuous operations. And actually, instead of calculating the number of something, we can look at some spaces and some algebraic structures on the space of quandle presentations of some knots.
Right. Yeah, it's certainly. So I bet this is way stronger way to look at it, right? So, but I don't know. Yeah, I should probably look closer at all these more complicated invariants. But so we are mostly interested actually in finite quandles because, like from purely mathematical, from purely algebraic viewpoint, even the finite case is very interesting. Well, and that goes back to the last point which I have here. So these kinds of structures were some of the first algebraic structures which were non-associative and appeared in mathematics. So the notion of distributive quasi-groups appeared already in 1920s in works of some German mathematicians. So they studied actually a symmetrized version of this definition, something structures where both left and right translations are automorphisms. So they call that distributive quasi-groups, and well, this is a special case. And also in Ukraine, Sushkevich, I think in Kharkov, he was studying these kinds of structures for some reason. So and they were already interested in finite quandles. Well, in putting some similar analogy to the theory of finite groups, I would say. So that was their motivation at the very beginning, and it's still an interesting motivation nowadays. Okay, so here are some more details about the two classes. So once again, I mean the definition. So affine quandles means affine combination over an abelian group considered as a binary operation. And well, if you want to study affine quandles, then I think the best way is to translate everything into module theory, to consider those structures as modules over the ring of Laurent polynomials. And yeah, and then the methods of commutative algebra quickly give you answers, or maybe not so quickly, but give you at least in principle answers to pretty much any questions you can have. So for instance, you can quickly tell for which pairs of AF give you isomorphic quandles, or there is an enumeration up to size P to 4. Okay, so things like that have been done using commutative algebra. Well, and there is a connection between coloring by affine quandles and the Alexander polynomial. So this is a theorem which I like to cite, which explains how that works. So if the Alexander polynomial is 0, then your link is colorable by every affine quandle. If it is 1, if this means trivial in some sense, then it's not colorable by any affine quandle. And if it's if none of the two trivial cases is true, then actually it is colorable by some affine quandle, but not by every affine quandle, right? And the affine quandle can be taken. I mean, the group will be just the Laurent, the ring of Laurent polynomials by the Alexander polynomial. Okay, so this is one expression of the connection, and I think there are more theorems of this sort. Okay, so I think one shall remember that coloring by affine quandles is essentially the same thing as calculating the Alexander polynomial. So, So that's maybe, so the affine quandles are maybe not so interesting for coloring in a way, okay? The Alexander polynomial is well known. Okay, so what about the conjugation quandles? So this is an important example because of Cayley representation. So if you consider the symmetric group over Q, so have a quandle with a base set Q, and consider the symmetric group over Q, and consider the mapping that you use in the Cayley representation of groups. So you take an element X and you assign the left translation of this element. This is a permutation, right? It's actually an automorphism. Well, and this mapping actually is a homomorphism, which is a very interesting property, right? So this means that the left translation of X star Y equals LX LY LX inverse, right? You do conjugation operation here. So well, this is something certainly to be exploited. So there is a theory which somehow exploits this connection. So it works very well for so-called faithful quandles. So a quandle is called faithful if this mapping is actually injective. So then everything is so then faithful quandles are essentially subquandles of conjugation quandles, and well, there's well, you can use this fact, right? I mean, you have some concrete representation, and that's useful. On the other hand, this is kind of rarely true. So the Cayley map is quite rarely injective, and then you can develop the theory of extensions, right? So you factor by the Cayley kernel, and then you represent, and maybe you iterate this process, and you can essentially have a like tower of some tower which goes towards your quandle, and then each factor is behaves good, and well, this can be exploited. So Michael Eiserman was a proponent of this approach. So he has some papers a couple of years ago where he uses this approach to quandles in detail. And recently with Marco Bonato, we did some algebraic theory which explains slightly better some of the phenomena. Okay, so that's certainly a possible approach to quandles. So here's the connection to what you are talking about. So it's if you have a non-trivial knot, then it's certainly colorable by a conjugation quandle over the group SL2P for a certain prime number. Okay, so this is essentially a theorem by I think Kronheimer and Mruvka, and what Greg Kupperberg did is that he somehow figured out that if you project their general result with these continuous groups into finite fields, then that it gives exactly this statement. So that's so in theory, like for this knot recognition algorithm, what you can do, you can just consider all possible conjugation quandles over these SL2P groups, and you will be fine. The question is, if you have two inequivalent diagrams, then how big the P must be so that you get a distinguishing invariant, right? So this is not clear, but at least in theory, you can restrict to these kinds of quandles. Well, and when I say conjugation quandle over this group, then I mean actually to take just one conjugacy class, so that.
Well, excuse me, and isn't it just a logical corollary from Kronheimer-Mruvka? I mean. So if we can impose some condition, and so if we see that, for example, there is some condition between arcs, and it should have an appropriate length. And for example, if we know that it doesn't happen for length which is less than 1 million, then we can be sure that for P less than or equal to, say, 2 to the 1 million, we will certainly get no relations. So relations appear for P small enough. So am I right that this result is more or less logical? More or less logical.
I think so. So it wasn't obvious to me when I was reading Greg's article, but maybe this is a very standard argument. So his paper mainly focuses on the last statement. So if the generalized Riemann hypothesis is true, then actually this P is never too big. Okay. And I think that was the more complicated part of his paper. So I could, yeah. So to me, all of the ideas were new when I was reading it. But I think he explicitly stated that that the main point is to notice that under the Riemann hypothesis, the P is guaranteed to be relatively small. I mean, polynomial size with respect to the number of crossings. Okay. So that's I think his main message. And again, yeah, so I'm not sure how difficult is the second part. He also says that it's kind of standard argument, but okay. So,
I'm not sure. I'm not sure. So I'm not sure participants here are very familiar to some ways how generalized Riemann hypothesis can be used in such problems. So can you say a couple of words about that?
So, so me neither. To me, so I met this generalized Riemann hypothesis twice in my mathematical life. This is one occasion, and another occasion was in analysis of complexity of some number theory algorithms. And in both cases, I think I could summarize the use like this. So let's say, well, you have some problem which is described in a certain kind of language. And now I cannot say what is this kind of language. And let's say this problem has a solution modulo some prime. Then the generalized Riemann hypothesis implies that this prime will be relatively small. Okay. And now I don't remember, and I think I never fully understood what kind of problems have this property and what does it mean to be small. But in this concrete case, so the problem of coloring by these SL2P quandles reduces to solving some polynomial equations. And if these polynomial equations are solvable modulo some P, then somehow by this Riemann hypothesis, the P is guaranteed to be relatively small with respect to, I think, the number of variables or something like this. So this is roughly the idea, but I don't know more about that.
Okay.
So and in these number theoretic algorithms, this was something similar. So what was that? Yeah, I think it was essentially the same problem. Again, it was so the problem which I was reading about was again reduced to essentially some polynomial equations, and then the question was modulo which prime these equations have a solution, and the Riemann hypothesis was used to show that this prime will be relatively small.
Okay.
Okay, so. Another type of quandles which appears frequently in literature are simple quandles. So they are simple in the sense that like groups are simple and rings are simple. So there are no non-trivial homomorphic images. Every homomorphism from Q is constant or bijective. Okay, so that means simple or well injective. So in other terms, this means no congruencies. Like congruencies are, well, I will come to that later. So the classification of finite simple quandles is known. So it's been done by David Joyce already in 1980s, and you can find a nice exposition in this famous Andruszkiewicz and Grania paper, where you can find a lot of basic theory of quandles. And actually, finite simple quandles are completely classified, and there are two families of them. One is affine, and the other one is actually conjugation quandles of certain special type. Okay. So the two examples that I mentioned previously, they actually are like the only two constructions that are used in this classification, right? So and again, like an observation, a simple observation is that if you have a non-trivial knot, then it certainly admits a coloring by a finite simple quandle. Okay, and this is a simple proof that if there is a non-trivial Q coloring, then you can project this Q coloring onto every factor, and somehow it's not difficult to show that at least one of these projections must be non-trivial. So yes, so for the knot recognition algorithm, I mean, if you want to distinguish a and the AND knot, the trivial knot, then you can focus on simple quandles. That's fine. Okay. So yeah, that's another interesting class. And you see, I mean, the group theory starts playing a role because, well, here are simple groups, right? So this is a conjugation class in certain powers of simple groups. So
excuse me, I have a question. So since a long ago, I had an idea that one can upgrade the Quandle to have two operations for early overcrossings and late overcrossings, which could potentially detect non-invertibility, which is, well, a problem for usual Quandles. And actually, to that end, I needed something like a reducible or simple, I don't know, Quandles. So I need actually two operations which are similar but not the same. And actually, I'd be happy to discuss it later.
So this may so if you have, even if you have two operations which are, let's say, both Quandle and they are somehow naturally related, I think the number of simple objects in this class will be way bigger. So I think this this theorem is very I think it doesn't naturally generalize beyond Quandles, but we can discuss.
Okay, thank you.
Maybe there's something to say about it. Okay, and here are some other important classes. Oh, sorry, that should have been the title. Okay, there's plenty of special classes of Quandles which appear in literature. So let me just pick 2 or 3 of them which appear frequently. So I'm mentioning the medial Quandles firstly because I mean, we wrote a paper about it, and also because you might have seen this identity somewhere. So this identity has many names, like many people call it by many different names. Abelianness is the T identity, it's entropy, it's I don't know. So it again, it like shows up naturally in mathematics. So I just want to display it so that if you accidentally came across this equation in the case of Quandles, then we call it medial Quandles, and we can say a lot about this special type. Okay. The more interesting class, which I'm going to talk about longer, very soon, are connected Quandles. Okay, so a Quandle is called algebraically connected if every pair of elements A and B can be connected by several left multiplications, by applications of several left translations. Right. So you take A and you multiply it on the left a couple of times, and you get to B. As long as for every A and B you have a way to get from A to B, then the Quandle is called connected. Well, and if you are coloring a knot, then of course, if you start with a color of one arc, then all of the colors will be in the same component of connectivity. Indeed, that's the condition says. So from the viewpoint of coloring knots, only connected Quandles are interesting. If you color links with more components, then of course you want to consider arbitrary Quandles. But for knots, this is an interesting special case. Another interesting special case is something called Latin Quandles. These are Quandles such that when you write down the multiplication table, then you get a Latin square. Okay. So you can make a multiplication table by, so if you have elements 1, 2, 3, 4, let's say, then you have a 4x4 matrix, right? Which displays what is the result of the operation. And if this is a Latin square, then we call it a Latin Quandle. So if this means algebraically that both left and right translations are permutations, right? And they are indeed connected because from every A to B you get through this element which results from right division. So this is a special case of connectedness.
In your definition of connected Quandles, did you switch multiplication? I thought that I would get from A to B by acting on A by the Quandle element.
So so I'm using the left notation, I think, consistently throughout the slides, I hope. Yeah, so
okay, maybe I just wasn't paying attention to your notation initially.
Right, I'm applying left translations. So for me, the interesting ones are the left translations and yeah.
Okay, fine.
Yeah, I think in your notation you just mirror everything and replace stars with triangles, and that's it. Sorry about it. Yeah, there's plenty of notation systems for Quandles, so I'm using mine, which is yeah, one of the many options. So
Yeah. I'm sorry. I hadn't paid attention on your first slide. Excuse me. Yeah, fine. Okay, good.
okay, so these are some of the other classes that appear frequently. Okay, and so I will focus on the class of connected quandles, and I will show how group theory can be used to actually tell something about this special case, and at least in principle how to classify all of connected quandles and more, right? Well, essentially. I will show how to translate problems about connected quandles into problems about transitive groups. So as much of the theory of transitive groups you can do, that much problems you can solve, okay? So this is, in a way, it's nice because if you want to know something about quandles, then you translate the problem and you ask a group theorist to help you, okay? So that was our idea when we attacked some of the problems and didn't know how to proceed. Okay, so here is the idea how to connect quandle theory to group theory. Okay, and again, there are several approaches. This is one of them. Okay, so one approach is through the so-called structure groups, and which are somehow finitely presented groups using some natural relations. But I'm not going to talk about that. Some people are using this approach, but I will stick to the theory of finite groups. Okay, so. You have these left translations, which are automorphisms. So let's generate a group, right? So it will be a subgroup of the group of automorphisms. You generate a subgroup from the left translations. Okay, so this is called the inner mapping group in some terminology. In our terminology, which comes from this algebraic combinatorics, this is called traditionally the left multiplication group. It's the same object. Okay, so this is a very natural thing to do. Okay, you have some permutations, so let's generate a group and see what happens. What is a less obvious choice is to consider so-called displacement, or some people call it transvections. So instead of a translation, you will consider the displacement. You will just compare Lx and Ly inverse, right? And then this element is an interesting permutation. So let's generate a subgroup by these mappings. Okay, so I will call it the displacement group. Well, and interestingly, many, or if not most, interesting properties of quandles are determined by the properties of these two groups. Some simple properties are determined by from a single one, but some more complicated properties are actually expressed in like combined properties of these two groups. I mean, in the way how the displacement group is embedded in the multiplication group. So the general pattern of results is that a quandle Q has some property, let's say property X, if and only if the displacement property, the displacement group has property Y, and the multiplication group has the property Z. Okay, and there's various kinds of logical conditions you can imagine, right? So somehow these two groups determine a lot of properties of quandles, and especially in the case of this Q, it's not at all obvious that this is an interesting group. So for example, the quandle is medial if and only if this displacement group is abelian. So it's not that easy to read the mediality from the multiplication group, from the natural one, but it's actually very easy to read this medial identity from the displacement group, right? So this is maybe the simplest example I can imagine. Right? A quandle is connected if and only if this multiplication group is transitive. Okay, that's kind of obvious from the definition, right? So by consecutive application of left translations, you can get from any point to any other point. Okay, so that's transitivity. But this is actually equivalent to transitivity of the displacement group, and actually both groups have the same action on Q. So okay, and there's many more examples of that. I will tell some of you later. For example, a quandle is solvable in the sense of commutator theory from universal algebra if and only if the displacement group is solvable, which is actually a very complicated theorem. Okay, so this is another example which I will show later. Right, and so here is what this correspondence does for connected quandles. Okay, so this is another particular type of construction. So first consider a group, a subgroup, and an automorphism of the group which fixes the subgroup element-wise. Okay, so let's have a configuration like this. You have G, H, and psi. H is a subgroup, psi is an automorphism which fixes H pointwise. And then take an operation which is defined like this. So this is some analogy of the affine combination of A and B in the non-commutative setting. Okay, it's a relatively natural thing, although it may not seem so. So define this operation on the cosets of G over H. Okay, so this looks like an arbitrary construction, but it's actually not. It's actually very general, and every connected quandle is isomorphic to a quandle of this kind. Okay, so this is a universal construction for the class of connected quandles. Okay, and this has been noticed, I think, by many authors, including David Joyce, and much earlier, well, slightly earlier by Galkin in the setting of Latin quandles and so on. So it's been reinvented a couple of times. And this is a very useful thing. Okay, so we have a concrete representation. So actually, not only every connected quandle, every homogeneous quandle can be represented this way, and that's why homogeneous representation. So this represents precisely the homogeneous quandles. Yeah, let's not get too much into details. And this can be this fact can be exploited in finding a one-one connection to some configurations in transitive groups. So the following theorem we formulated with my colleagues a couple of years ago, and it's not deep at all. I mean, this is essentially well, it's not difficult to prove on top of this important observation. That connected quandles are in one-one correspondence with certain pairs. Okay. So the trick is that you want a one-one correspondence so that you can produce a classification, for instance, enumeration. Okay, so connected quandles are in one-one correspondence with pairs G zeta, where G is a transitive group and the zeta is a certain element of this transitive group. Okay, it should be a central element in the stabilizer of a point, and the conjugacy class of this zeta should generate the whole group. Okay. So whenever you have a pair G zeta such that G is transitive and zeta satisfies these conditions, you have a connected quandles, and well, there is one-one correspondence. Well, and then we can solve the isomorphism problem, like two quandles on a given set Q are isomorphic if and only if these two pairs of G zeta satisfy certain conditions, which are fairly easy to verify. Okay, so this is our approach to classification of connected quandles, to producing examples. Well, and here is an example of what you can do with this classification. So, for instance, there is a theorem from 2001 which says that connected quandles of prime size are affine. So, whenever you have a prime number of elements, I mean, only the affine construction is going to work, nothing else. Okay, and the original proof was actually quite complicated, and our proof is essentially the same, but it can use some group theoretic results as black boxes, right? Because we have a proper group theoretic setting, a good terminology, so we can just pick the results we need. While these three very famous mathematicians, I mean, they did a complicated argument, which we could have never done, but we were in our simple argument, we were guided by this correspondence. Well, and what the sketch of the proof, just to give you an idea what kind of theorems you can use. So you have so if you have a prime number of elements, so you have a transitive group which acts on a prime number of elements. Well, so that means that the group must be primitive. Okay. Well, and then exactly for this case, there is a theorem of Kazarin from 1980s, which says that if you have a group and you have a conjugacy class which has a prime number of elements, then this conjugacy class generates a solvable group, right? And that exactly fits our situation. When G is the multiplication group, then the conjugacy class is well, that's exactly the size of the quandle. Right, so we see that the multiplication must be solvable. Well, but if you have a primitive group which is solvable, then well, again, there is an old theory which says how these groups look like. This goes back to Galois, and Galois proved already in 19th century that primitive solvable groups are affine. So you have an affine multiplication group, and then there is only a few steps to show that then actually Q must be affine. Okay, so you see, I mean, as a black box, we can use some relatively new theorem from the theory of transitive groups and some old theorem of Galois. So that's the type of arguments which you can at least in theory do. Okay. Well, and again, I mean, as I'm a computational guy, so I like concrete numbers, small numbers. So this is the number of quandles of given connected quandles of given size. And how did we do this table? So we count all of these pairs transitive group and this zeta up to conjugacy. So the isomorphism of the corresponding quandles goes back to conjugacy of these pairs in some concrete sense. Okay, so we can calculate the number of connected quandles of given size, and we can even construct them in an explicit way as long as we have a database of transitive groups. Okay, and there is so currently Derek Holt produced the list of transitive groups up to degree 47. So therefore we can classify all connected quandles up to size 47. And you can do more, so like you see that there are some patterns, like if you look at the size which is twice prime, then there are none except 4, 6, and 10. So like twice 7, you get 0, so 14, 21, 22, I don't know, 38. Okay, you see plenty of zeros, so all of these zeros are of type twice prime. And there are no connected quandles of this size except for sizes 6 and 10. And well, this follows quite quickly from the Owen and Scott theorem, as we noticed in our paper, which is again like a much shorter argument than the one that appeared earlier in literature. Okay, so that's an example of theorems you can prove. And here's my favorite open problem. Hayashi noticed the following thing. So he was playing with multiplication tables of small connected quandles. Okay, and then if you look at the rows, I mean, these are permutations in the multiplication table, right? So if you look at the left translations, you get a list of permutations. If the quandle is connected, that means homogeneous in particular. So all the left translations have the same cycle structure, right? So maybe they have 3 cycles of length 1, 3 fixed points, and 5 cycles of length 2, and maybe 1 cycle of length 5. Okay. So all of these translations have the same cycle structure. Well, and then he noticed that actually the length of every cycle divides the length of the longest cycle. Okay, so actually the example which I said is not possible, right? You cannot have the longest cycle of size 5 and at the same time some cycle of size 2, okay, of length 2. Okay, so this is the conjecture which we noticed by inspecting lots of examples. Well, so now prove it, right? I mean, this is still open after many years, and I know a few people who are looking at the problem, including myself, and we have essentially no idea whatsoever. Well, and this can be translated purely into a group theoretic statement, right? So if you want to give it to a group theorist who's totally disinterested in quandles, you can tell him the following problem. So if you have a transitive group and over a finite set, and you have some element zeta, which is in the center of the stabilizer, and its conjugacy class generates the whole group, then this cycle condition holds. The length of every cycle divides the length of the longest cycle, right? I mean, there are no quandles in this definition whatsoever, and it's a relatively natural group theoretic statement. Okay, so this is a this is one way which I look at quandles. Okay, at least connected quandles are some configurations in transitive groups. And as long as you can do finite group theory, you can prove things about finite connected quandles. Okay, so that's one message which I wanted to tell. Okay, and the second topic is how you could possibly use universal algebra. Okay, so what is the motivation? So The motivation is that maybe you want to use inductive arguments, like in finite group theory, for special types of quandles, which would have some inner structure which resembles, let's say, solvable groups or nilpotent groups. Okay, so in finite group theory, there's a lot of interesting theory which is based on existence of certain series, and solvability and nilpotence is the prime example which is taught in the elementary group theory course. So I thought, well, maybe some theory like that would work for quandles too, and we could prove some theorems using it. Let's say if you want to classify small quandles, right? If you look back at this table, then indeed, well, it's maybe not obvious, but it looks like the biggest numbers are when you have big exponents in the prime decomposition, right? Like for groups. I mean, if you look at the number of finite groups of size n, then the number depends mostly on the largest exponent in the prime decomposition, right? So how do you do classification of finite simple groups? If you want to know, for instance, all groups of size 16, so how do you proceed? Well, first you prove that all of them have to be nilpotent, and then you do some inductive arguments and some recursive constructions, and that's how you can eventually classify them. Okay, so I thought, well, maybe the same theory for quandles would allow us to classify, let's say, all quandles of size pq, where pq are different primes, or maybe all quandles of size p cubed, right? Okay, so that was the idea. So as you see, I mean, the quandles of size p square are still affine. So maybe all quandles of size p cubed will be some kind of nilpotent, and they will be obtainable by some kind of central extension, right? Like for groups, maybe. So that was our idea. That was our motivation. But then, what is a solvable quandle? What does it mean, a nilpotent quandle? Right? What is the proper definition that could be used for these inductive arguments? That's not clear at all. Well, so in universal algebra, universal algebra has an answer to these questions. But first of all, before I proceed to these more complicated notions of solvability and nilpotence, I have to tell you what is an abelian quandle, right? And then now abelian should be in the sense of like a well, so solvability and nilpotence uses abelianness in some way to define these notions, right? So what is this magic notion of abelianness which gives a good notions of solvability and nilpotence? Okay, so here is a theory. So this will be a like a very brief sketch of what is the main idea behind this universal algebraic commutative theory. So what makes abelian groups so special? Okay, so the basic idea is that it's not commutativity which makes abelian groups special. Okay, so commutativity is a syntactic condition, but it actually doesn't make the group special. What makes their structure special is that they are actually modules. Okay. So abelian groups are Z modules. Okay, so this is what makes them special. Well, so we need a universal algebraic condition, so like an abstract condition which would work for arbitrary algebraic structures, which somehow exploits this idea that abelianness should mean that it looks like a module in some sense. Okay, and it definitely doesn't have anything to do with commutativity, right? It's this like proximity to two modules. Okay, so that's the idea. Well, and here is an approach which proved immensely useful. So it was pioneered by Jonathan Smith in 1980s, and he proposed the following definition. So if an abstract algebraic structure A, so it means just a base set and a number of operations on that. They don't have to satisfy any particular axioms. Okay, and then this algebraic structure will be called abelian if the diagonal is a congruence block of a square. Okay, so take the direct power and you look at the diagonal, and if this is a block of a congruence, then we will call this structure abelian. Okay, so it's a simple exercise in elementary group theory that a group is abelian if and only if the diagonal is a normal subgroup of a square, right? So the fact that the diagonal is a congruence block in groups, this means that the diagonal is a normal subgroup. Right? The diagonal, I mean all elements of the sort AA. Right? So you might have seen this exercise somewhere. Well, and if you translate, then this is an abstract term condition. So some sort of quasi-identities, right? Some logical conditions which describe exactly this phenomenon. Okay. So and I don't think it's probably pointless to study this definition. I just want to show how the definition looks like, right? So it says for every term operation and every tuple of elements of A, some implication holds. So you plug in something into the term T, and this implies that something else holds. Okay, so it's this kind of condition. But and it's equivalent to saying that the diagonal is a concurrence block. So why? So this looks like an arbitrary definition, right? This is one of the many possible equivalent expressions that describe abelian groups among the class of all groups. But actually, this particular choice has very nice properties, as has been proved in the subsequent decade. Right. So there was a decade of results showing that this definition is actually very important. So and there is a thick book about this. So there are quite a few arguments telling that this is a meaningful approach. So essentially, so one observation is that whenever you have a module, then it is abelian. So all modules are abelian in this sense. And not only that, if you take a polynomial subreduct, then it's also abelian. What does it mean? This means that so what is a reduct? You essentially forget some of the operations, or maybe you define new term operations from the given ones. Okay, so that's called a reduct. Okay, so somehow define new operations using the old ones and forget some of those. Okay, and subreduct means that it's a subalgebra of reduct. Okay, so in some sense, this means that if you do this definition of new operation and you forget some of the operations, then from modules, then you get an abelian algebra. So this is an almost trivial observation, but the important thing is that it's almost always the opposite implication is true. So whenever you have an abelian algebra, one which satisfies this complicated definition, complicated syntactic definition, then under very mild condition, you actually are holding a subreduct of a module. Okay, so here is a brief summary. So the converse application is false in general, but known counterexamples are rare and unnatural. So this Quackenbush's construction is very combinatorial, and it has probably no good meaning in any other theory. And the converse implication is true under very mild assumptions. And in particular, it's true for quandles. Okay, so that's so the fact that it's true for quandles is a beginning of a possibly positive story. That somehow the definition makes sense in the class of quandles. And so let's see if the derived notions of solvability and abelianness also make sense. Okay, so that was the beginning of our project when we actually managed to prove that abelian quandles, in the sense of that definitions are subquandles of affine quandles. Okay, which is the realization of this notion in quandles. So so here are the theorems. So just to briefly summarize, so what we could prove that a quandle is abelian in this universal algebraic sense, if and only if it's a subquandle of an affine quandle. And again, in this condition has a very natural description using the displacement group. Okay, so remember I was telling you that you can read from the displacement group almost every interesting property of a quandle. So abelianness is another example. So this is if and only if the displacement group is abelian and semi-regular. This means that no permutation has a fixed point except for the identity. Okay, the identity is the only permutation with fixed points in this group. Okay, and then just a slight modification of this theorem is that is one which characterizes actually affine quandles or Alexandre quandles. I mean this affine construction. Right? This is equivalent to being abelian in the sense of universal algebra, and a certain balancedness condition like the orbits of this Q must have must be some balance in some technical way. Okay, so and again, I mean, we have for this balancedness, we have some group theoretic condition. Okay, so that was the beginning of the story. It looks like the universal algebraic commutative theory has a good meaning in quandles. So okay, so I'm not 100% sure that everybody is familiar with using congruencies. So in what follows, I have to use them. So let me briefly explain what is a congruence. So have an abstract algebraic structure, and congruencies are kernels of homomorphisms, which means the set of pairs AB such that the homomorphism has the same value on A and B, right? And equivalently, the first isomorphism theorem, these are equivalencies on the given algebra such that the quotient algebra, the factor algebra is well defined. Okay, so this is the very definition of a congruence. It's an equivalence such that it can be used for factoring. Okay. So for example, in groups, congruencies correspond 1-1 to normal subgroups, right? So what are the equivalencies are given actually by the decomposition to cosets, right? So if you have a normal subgroup, then how do you get a congruence? Well, you look at the coset decomposition modulo this normal subgroup, right? And the other way around, if you have a congruence, then just look at the block which contains the unit element, and well, you get a normal subgroup. Okay, so in groups we don't need congruencies. In rings we don't need congruencies. In modules we don't need congruencies because they are in 1-1 correspondence to certain subobjects. But in general we do need congruencies for general algebraic structures. In quandles there is no 1-1 correspondence to any kind of subobjects. But we have some sort of weak correspondence, which we found out with my colleague Marco Bonato, and that was the beginning of translation of the commutative theory into quandles. Okay, so now how to define solvability or nilpotence in abstract algebraic structures like quandles? Okay, so look at the definition of for groups, right? For inspiration. So a group is called solvable if there is a series of normal subgroups such that, right? It's an increasing series of normal subgroups such that the factor of the two corresponding subgroups is abelian, right? And how do you define nilpotence? I mean, the pattern is the same, and instead of abelianness, you have centrality, right? So the factor is in the center of this factor group. So that's one of the many possible definitions of solvability and nilpotence. Well, so how would you generalize? So into general algebraic structures. So instead of a group, you will have a quandle or an abstract algebraic structure A. And instead of normal subgroups, you will have congruencies. So we will have a chain of congruencies, and such that the factor of the corresponding of the two adjacent congruencies has to satisfy some certain abelianness condition. Okay. So so that's the definition, right? So there exists a series of congruencies, right? A increasing chain of congruencies, such that the factor congruence is abelian, respectively central congruence of the factor, right? So that's just a syntactic blueprint of the definition, and what we need to do is to define these notions of abelianness and centrality, right? So that's the key, right? As long as you can define what is an abelian congruence of an algebraic structure, or what is a central congruence, then you have a notion of solvability and nilpotence. Okay. Right. So the last okay, an alternative approach. You can have you can look at these series defined by commutators. And well, if you have a commutator, then you can define solvability and nilpotence by these lower series. Okay, so that again admits a natural generalization to arbitrary algebraic structures. So as I said, I mean, either you need a commutator or you need a definition of what does it mean that the congruence is abelian or the congruence is central. So here is the definition, and that was a continuation of Smith's work, which was later elaborated by others, and which is so if you want to learn more, then the main reference is a book by Fries and Mackenzie. which describes how to generalize from abelian algebras to abelian congruencies. So here is some centralizing relation. I don't want to go into details, just notice that it's a similar type of conditions that appeared on a slide earlier, right? So it's like a abelianness relative to a congruence delta and congruencies alpha and beta, okay? And then the commutator is defined as the smallest delta such that this condition is satisfied, okay? And don't study the details, just if you remember the definition of abelianness, then notice that it has the same pattern. So it's like a relativization of the notion of abelian algebraic structure into, sort of abelian relation between three congruencies. Okay. Well, and you can define a commutator using this condition, the smallest delta such that this strange relation holds. Okay. And then, of course, if you know what is a commutator, then you know what does it mean that something is abelian, right? Something is abelian if and only if the commutator of alpha is 0 and the smallest congruence. And what does it mean that something is central? This means that the commutator with the largest congruence is the smallest congruence. Okay. All right, so this is some abstract setting. So now, does it have any meaning? So yes, I mean, if you apply this to group theory, then you get the standard notions which you know from group theory. And this is not difficult to prove, but it's certainly not obvious. So this is a fairly complicated exercise in universal algebra. So, okay, but in group theory, it does give the same notions of commutator, abelianness, centrality, and therefore also solvability and nilpotence. Okay. Well, and then there is some theory in this Fries-McKenzie book, which says that this is going to work quite well in many types of algebraic structures. But remarkably, I mean, there are some assumptions like that the algebraic structures should have modular congruence lattices, which is actually not the case for quandles. So it is not at all clear that this works quandles well, but it actually does, and that's what we proved with Marco Bonato, and it's the paper just appeared in the Journal of Japanese Mathematical Society. And it's based on the following correspondence between congruencies and normal subgroups of the displacement group. Okay. And so actually the objects, so on one side you have congruencies, and on the other side you have, something slightly more complicated than I said. You have subgroups of the displacement group, which are normal in the multiplication group. Okay, so that's when I said that it's often the interplay between the multiplication group and the displacement group which determines the property of a quandle. Then this is an example. Okay, so to every congruence you can assign something we call relative displacement group, and to every n with this property you can assign certain congruence. Okay, and again the syntax doesn't make is not important, such that you get not a 1-1 correspondence, but you get a Galois correspondence. And we could prove that in this correspondence, this centralizing relation is satisfied for two congruencies, alpha and beta, if and only if, and here is again some purely group theoretic condition. Okay, so again, the concrete meaning probably doesn't matter, but notice that this is a purely group theoretical condition on these normal subgroups. Okay, one of them centralizes the other, and that there is some semi-regular action relative to one of the congruents. Okay. So okay, so that gives that gives essentially the translation of the universal algebraic notion, right? Remember that complicated term condition into something which is group theoretical. And therefore, you can use group theory to somehow work with this condition. Okay, so based on this proposition, you can define what does it mean that a quandle is solvable, that a quandle is nilpotent, right? That means this series of congruencies. And therefore a series of subgroups of the displacement group, which has certain particular properties. Okay. Well, and based on that, we could finally prove a few theorems, which are summarized on this slide. Okay, so on one side you have a quandle property, and on the other side you have a property of the displacement group, which is equivalent to it. Okay, so I already talked about a quandle being affine, right? So that means that the displacement group is abelian, it acts semi-regularly, and there is some balancedness condition. Well, then there is a weaker property of abelianness, which is equivalent to the fact that the displacement group is abelian and semi-regular. And there is, on the quandle side, there is the notion of nilpotence. I mean, that the universal algebraic definition of nilpotence. And with some effort, actually, we could prove that this is equivalent to the displacement group being nilpotent. Okay, and the same applies to solvability. Okay, and in the special case of finite connected faithful quandles, we could even prove the prime decomposition of nilpotent quandles. Okay, so under these additional assumption, a quandle is nilpotent if and only if it is a direct product of connected quandles of prime power size.
Excuse me, and is there any theory of solving some quandle equations in terms of solvability of quandles, like quintics and similar things in terms of Galois theory?
So in general, in universal algebra, there are some general results about solving equations over algebraic structures of certain kind. And the fact whether you can solve equations over some algebraic structures is determined by solvability or nilpotence of the structure. And I don't remember the results precisely, but it's often something like you can solve an equation over, let's say, a group in polynomial time if and only if I think the group is so if the group is nilpotent, then you can solve equations efficiently. If the group is not solvable, then the problem of solving equations is NP-complete. That means very difficult. And in between, if it's solvable but not nilpotent, I think it's open. So if you mean, and this generalizes from groups to some other types of algebraic structures. So if you ask about quandles and solving equations over finite quandles, then it's probably this falls between one of the known cases, but I'm not sure. Okay, but in Galois theory, actually, the problem is finer in the sense that you are not solving equations over the Galois group, you are solving polynomial equations, and then from these polynomials, I mean, to each of the polynomials, to each of the equations, there is an assigned group, and then you ask about the properties of this group, right? So this is maybe a different, so this is a different problem than what I was talking about. So, yeah, but yes, I mean, in general, these notions do have something to do with solving equations. That's correct. That's there is a theory about that in computational algebra. Okay. All right. So we have these new notions, and now the last two slides is so what this could be possibly good for, right? So I mean, we have nice abstract definitions, and okay, so maybe that's it, right? So we have some use for it. So for instance, my dream when we started the project was to come with these inductive arguments, simple inductive arguments. Okay, so there is a very interesting theorem from 1950s. It's one of the very first enumeration theorems, or how to say, like classification theorems in Quandle theory. I mean, long before quandles were born. I mean, this is an important theorem in Quandle theory. So if you look at Latin quandles of order congruent 2 modulo 4, right? So Latin quandles of size 4k plus 2. So there are none, okay? None at all. The original proof was very complicated. It was proved by Sherman-Steen, and this used a very complicated geometric argument. So somehow we took this discrete problem and translated it into some geometric question, some question in algebraic topology, and then using algebraic topologic methods, he was able to get a contradiction somehow. Okay, a complicated argument, an interesting one. well, at the same time, it's a problem about discrete structures. So obviously, I mean, there should be an elementary proof, right? Or maybe not obviously, but there should be one. Okay. So now Galkin was the next one to look at this theorem in 1970s, and he was the one to propose an approach through group theory. So so he thought, well, so instead of looking at these Latin quandles, let's look at the multiplication groups, and let's use some group theory to prove that. Well, and he was able to find some Silov argument that shows that there cannot be any Latin quandles of size 4k+2. Okay, so somehow the properties of these hypothetical multiplication group would contradict Silov theorems. Okay, but then I mean, you would say, so there should be a super simple argument by induction. So take the smallest example, and then well, let's find a smaller example, right? So our theory actually allows for such an argument. So it has two steps. One of them uses the classification of finite simple quandles. So first you show that, so let's have the smallest Latin quandle of this type. Okay, so first let's show that it's not simple, and for that you just use the classification of finite simple quandles. Okay, and you just verify that there is none of order 4k+2. Okay, so then your example is not simple. So if it's not simple, then it has a non-trivial congruence. Well, but then all blocks of this congruence have the same size, and the size of these blocks times the size of the factor must be 4k+2. Well, but the only option is that either the size of the block or the size of the factor is again congruent to modulo 4. Well, so that's a smaller counterexample. Okay, so this is a super simple argument. Which, however, requires that in order to make sense, requires the use of the classification. Well, and for the classification, actually, so what I said, I forgot an important assumption. I forgot an important assumption. I'm using the classification of affine simple quandles. Okay, and then so there are no affine simple quandles of size 4k+2. And the trick is that if you have a finite Latin quandle, then it's actually necessarily solvable. So somewhere in literature, you can find a theorem which says that if U is a finite Latin quandle, then its multiplication group is solvable. So actually, you cannot find a statement like that. So Alexander Stein, this is a different Stein, was considering some types of transitive groups. And he proved some group theoretic result, which in quantum terminology means exactly this. Okay. Well, and and this can be directly applied to finite Latin quandles. So you get that the multiplication group is solvable. Then by our theory, this is the same thing, that the quandle itself is solvable. Well, and therefore, if it is simple, then it has to be abelian. And if it is abelian, then it's affine. And by the classification of finite simple quandles, I mean, there is no affine simple quandle of size 4k+2. Okay, and then you can do the inductive argument. So yeah, so I was quite happy about this consequence. Well, and then other people like Marco was able to obtain some other classification results which are new actually. So like the classification of all Latin quandles of size pq, or all connected quandles of size p cubed. Okay, so these are the results that I was hoping for. I mean, these ones are quite non-trivial, but. Okay, so that was that's one success of the theory, and the last one. So again, I mean, we have this theorem that finite Latin quandles are solvable. Well, and therefore, if you have a knot with a trivial Alexander polynomial, then you cannot color it by any Latin quandle. Okay, so I think that this was observed by some people who were playing with the coloring invariants. But as far as I know, there was no proof of that statement. Okay, so we can prove that again by an easy inductive argument. So it's based on this theorem which I mentioned earlier, that if you have a trivial Alexander polynomial, then you cannot color by affine quandles, right? There is no non-trivial coloring, and just a simple induction shows that this applies to any solvable quandle, and this in particular includes every finite Latin quandle. Okay, which is, I think, new Okay, so that's it. Thank you very much for your attention and interesting questions. That's what I wanted to present.
Oh, great. Thank you very much for a nice talk. So I have left some questions on the chat line. Dear colleagues, please unmute your microphones and write on the chat line, ask questions, please.
So do you think that any of your techniques are useful for computing the 2- or 3-dimensional homology of the Quandle?
I don't think so. I was discussing that with Petr Wojciechowski. He looked at the problem of calculating these homologies, and I think he understands it relatively well. And I think he told me that he was able to calculate something with Sangyop. And if I remember well, he didn't use any non-trivial theory that we proved earlier. So it doesn't mean that he wasn't guided by the insight, but I don't think that he was using directly any of these approaches for that.
I see. Okay.
But then Petr is the one to ask these questions because he knows both theories.
I see. Okay. Thank you.
Okay. Any more questions? Comments, remarks, please.
So maybe I can comment on some of the questions in the chat, right?
Yeah, I'd be happy.
So reference to self-distributive quasi-groups. So a couple of years ago, I wrote a survey paper about self-distributive quasi-groups. So if you go to my website, then you can find it, or you can Google. I think the name is something like a guide to letting quandles or self-distributive quasi-groups, something like this. So this surveys some of the basic results. How to construct these letting quandles and what are the main approaches, and then references to more detailed studies. So I would suggest to start from that and then go to the references.
I'd be grateful to you if you send the link.
Yeah. So I will quickly find a link.
Okay. Thank you. Thank you.
Let me see. I think it's on archive. So yeah, I have it. So here we go.
Okay.
So most of the results are quite old and scattered around some old journals. So this one summarizes, I think, the main, including some old interesting Russian papers which are only in Russian. So that's a well, which are maybe easy to access in Moscow, but they're hard to access anywhere else. So like I like the old results of Belousov and Onoy, so that they lived in Kishinev in the 1970s, and they have some interesting results.
You see, we have this site mathnet.ru, so here you can.
Right. Yeah. I know. I mean, I have no problem with reading Russian, but maybe some of the non-Russian colleagues will be happy to.
Okay. Okay, please, any more questions? Well, if it's not the case, so let's thank the speaker again for a very nice talk. I learned quite a lot. Thank you.
All right, thank you very much for inviting me. I hope it was understandable.
Okay.
Very nice.
Thank you very much. Excuse me.